Hi, I'm Megan Hicks, and along with Chris Lurson and Antareep Sahu, we are going to present on security API misuse in Python libraries. The mantra, "Don't roll your own," is prevalent throughout the information security community. What this means for developers is using well-researched and proven cryptographic APIs in their implementation instead of developing their own security code. This results in secure information exchange between systems. However, these APIs aren't perfect, and there are a variety of ways developers could misuse them. This paper focuses on 3 Python libraries: Cryptography.io, PyCryptodome, and PyNaCl, and evaluates their API implementations to identify possible vulnerabilities that could occur. Today, our agenda includes talking through the abstract as an overview, giving you an introduction to the topic, looking at some background and related research on APIs and some of the research that's been done on them, look at the specific libraries that we researched, look at some comparisons of those libraries, and review some misuse examples that we found and what kind of threat that poses, and then we'll conclude for the presentation. As an introduction, many libraries are available, and they range in what they offer. Some are kind of a plug-and-play option, and some are more low-level, fill-in-the-parameters options that may provide necessary flexibility for seasoned developers. Developers' decisions impact the level of security offered by an API. And a last question is, do APIs offer security to the developer through high-quality programs, defaults, instructions, and examples? That's what we set out to try and uncover. This is a list of some of the papers that we read in preparing to look at APIs and misuse of APIs. We looked at comparing the usability of cryptographic APIs, Developers Deserve Security Warnings 2 on the effect of integrated security advice on cryptographic API misuse, an empirical study of cryptographic misuse in Android applications, CryptoGuard, high precision detection of cryptographic vulnerabilities in massive-sized Java projects, and finally comparing the usability of cryptographic APIs. The first paper I'm going to talk about is called An Empirical Study of Cryptographic Misuse in Android Applications. And they looked at Android applications and cryptographic misuse, and they found that 88% of applications make at least one mistake in using cryptographic APIs. And as you can see on the chart, actually, if they make one, they often make 2, and some made even more. They developed CryptoLint to perform static analysis of common errors. And what I find most interesting is it was the first study to perform at scale and shed light on what looks like a widespread problem, and it also identified a likely root cause. The next paper we reviewed was called CryptoGuard, High Precision Detection of Cryptographic Vulnerabilities in Massive-Sized Java Projects. And they designed a set of cryptographic analysis algorithms to look at SSL TLS API misuses. And the goal was to improve detection accuracy of API misuse by reducing false positives using something that they called refinement insights. And they looked at 16 vulnerabilities, allowing for 5 types of attacks. And what's most interesting, I thought, was most common vulnerabilities in the Apache code that they were looking at were hard-coded keys, and they were thought to have been used in test code, but then accidentally packaged into production code.
I will discuss about the paper High-Level Cryptographic Abstractions. Kane et al. Discusses various misuses in cryptographic libraries and have proposed a high-level abstraction, sec-algo, implemented in Python to help developers write code. This is done to reduce difficulty of using low-level cryptographic libraries. We learned about 7 areas of API misuses which we could explore for Python APIs. They are insufficient key size, hard-coded keys, ECB mode of operation, encryption with predictable IV, encryption with obsolete algorithms, RSA encryption without optimal asymmetric encryption padding, hashing with obsolete algorithms. One interesting finding in this paper is that they have also listed the total number of applications that have API misuse in the year 2019 by various API misuse analyzing systems. For example, Cryptolint, CMA, CNKX, and CDRIP. This can be found in the table. I will discuss about the paper Secure Coding Practices in Java, Challenges and Vulnerabilities. Meng et al. Have studied about API misuses in Java programming. This has given us valuable insights into the area of API misuses. We were able to find similarities in Python APIs due to the fact that underlying cryptographic algorithms are platform agnostic. They provide valuable recommendations for people in all fields of software development industry, which definitely applies to Python programmers as well. Developers should perform security testing before their software implementations. Often testing is done by disabling the security features which can have detrimental consequences in the real world. Library designers should disapprove APIs with compromised security and should also provide adequate error reporting with root causes and relevant solutions. Tool builders are advised to build proper diagnostic tools to identify bugs and recommend patches.
One of the best background papers we reviewed for this project was comparing the usability of cryptographic APIs. The main discussion was how bad APIs can be and how they get too complicated, have insecure defaults, and are poorly documented. The paper goes into detail about how the design and usability of different cryptographic libraries affect the security of the code. The main goal of the paper was to help readers understand how to build effective libraries for the future, and the most interesting part was examining functional code from cryptographic developers and the correctness and security in comparing their results to their personal opinions on the different cryptographic libraries examined. The paper outlined how 20% of the developers who believed their code was secure actually had faulty code. The most successful libraries were the ones that were more than just simple and convenient interface, and also ensured support for a broad range of common tasks and provided accessible documentation with a secure and easy-to-use code examples. Another paper that followed along with comparing the usability of cryptographic APIs was the paper Developers Deserve Security Warnings Too: The Effect of Integrated Security Advice on Cryptographic API Misuse. This paper demonstrated the effectiveness of API integrated security advice for developers, and it informed them about common API misuse and places secure programming hints as guidance in the developer's IDE. This aims to solve the problem of developers being faced with too many complex programming choices with security implementations. This paper identified features lacking across various APIs, including easy-to-use documentation or meaningful warnings and error messages, as well as addressing insecure cryptographic choices, including encryption algorithms, key sizes, modes of operation, and hashing algorithms with helpful documentation in the guise of warnings.
The libraries we decided to review for our paper are Cryptography.io, PyCryptodome, and PyNaCl, which are all popular libraries used with Python coding.
The first library we researched is called Cryptography.io, and it has a goal to be your cryptographic standard library. It supports Python 3.6 onwards and PyPy 3 7.2 onwards, and its initial release was in 2014. It offers high-level recipes, is what they call it, and also low-level interfaces, and it provides for both beginner and experienced developers.
I will talk about the PyCryptodome library. PyCryptodome is a self-contained package of low-level cryptographic primitives which supports Python 2.6, Python 2.7, Python 3.4 and newer. It is almost a drop-in replacement of PyCrypto. It can be said that it is essentially a fork of PyCrypto, and a newer library of PyCryptodomics is also released. Most algorithms are in Python, and very few performance-critical components are in C.
The next library we're going to talk about is PyNACL, also known as PySalt, and it's built off of NaCl, also known as Salt, which is the C binding for that library in Python. So the background of Salt is written by Daniel Bernstein, who's a renowned cryptographer with the mission to make it easy for developers without deep knowledge of crypto to make safe encryption for their applications. What differentiates Salt from other cryptographic libraries is its use of elliptical curve cryptography, specifically using curve 25519. This curve differs because it uses 128 bits of security compared to older methods like RSA based. And so PySalt can get as low as 32 bytes, which helps performance. Another interesting note is PySalt also has better interface than other libraries considerably, and so with its simplicity it makes it really effective. PySalt's a Python binding to libsodium, and so it's a cryptography library written in C, and libsodium is the fork of the networking and cryptography library, SALT, which is mentioned earlier. This library is described in documentation as a high-speed software library for network communication, encryption, decryption, signatures, and more. And PySalt also supports Python 2.7 and then Python 3.5 and above, making it readily accessible for mainstream Python applications.
This chart offers a comparison of the different libraries and the amount of choices that it allows for the developer. And the main thing you'll notice here is that particularly in symmetric encryption, PyCryptodome doesn't offer any choices. They make the decisions for the developer, whereas cryptography and PyNACL offer a little bit more choice there. And of course, as you'll see, that choice can be a double-edged sword. So some specifics around cryptography.io is, as I said before, it has a stated goal of providing more usable security than other libraries. And it offers a high-level recipe option called Fernet for new cryptographers that takes a little bit of the guesswork out of doing things, since most of the decisions are made for the developer. It also offers low-level cryptographic interfaces for more knowledgeable developers. And it is closely managed for security issues and receives regular updates to manage security. It also is an open source project.
How does PyCryptodome compare? It is a healthy, secure, and sustainable Python API. On GitHub, it is widely downloaded and actively supported by the library designers with regular releases of improvements and necessary corrections. Cryptography.io and PyNACL are both built on C code. However, PyCryptodome, as already mentioned, is mostly built on Python, with a few performance-critical components in C. PyCryptodome is quite easy to use, and the documentation is also quite easy to comprehend. PyCryptodome supports most of the popular cryptographic algorithms, for example, ciphers, encryption algorithms, digital signatures, hashing, key generation, and other cryptographic protocols.
PySalt is described by the cryptography community as a modern and safe, as well as actively preventing mistakes to break your encryption. It's used specifically as one of the safest options for digital signatures, secret key encryption, public key encryption, hashing, message authentication, password-based key derivation, and password hashing. PySalt will simply call the C code underneath the binding, so typical uses for it can also include MAC verification and curve point addition, as well as support for ECC signatures and encryption. So now I'm going to show a table of the most popular featured programs utilizing PySalt. So in this table, a really interesting thing that I saw was an application for the Discord Pi package, which allows mods on Discord, which is similar to Slack. Allows them to have Discord server management and making bots, and allows security for those features so they can manage their servers effectively and securely.
Looking at misuse and threats in cryptography, what we found, which is probably not unusual, is that the more choices people have, the more options they have that might cause them to make a mistake. And the three areas that we looked at here to focus on in cryptography were the constant initialization vector, also weak encryption algorithms that are still available on the website for use, and also symmetric encryption. So with the IV vector, the empirical study for cryptographic misuse in Android applications found almost 2,000 applications out of 12,000 used a constant IV. And additionally, CryptoGuard also saw results with 40 IV constant errors in Apache programs. And this type of error could cause susceptibility to a dictionary attack. With the weak encryption algorithms, cryptography still offers Blowfish, ARC, and IDEA to developers because sometimes they're needed in an older program and people don't want to update to a new algorithm. And with that, though, some people may find that they can use that and they think they know how to use it safely. However, another study, the usability of cryptographic APIs, did find that even people who thought that they were well experienced, that didn't always correlate with highly secure code results. And this type of problem, these algorithms, could make code susceptible to a birthday attack. And then finally, symmetric encryption definitely requires more choices by the developer. You have to pick a cryptographic algorithm, a mode, an IV, and a backend, and an HMAC. And all of those things offer the developer another chance to possibly implement in an insecure way.
In this slide, we will discuss about cryptodome misuses. For encryption using asymmetric RSA algorithm, the API allows the private key to be exported in the clear without a passphrase. We will demonstrate this in the next slide. Second, ECB mode of encryption is available but not recommended at all due to existing vulnerabilities. In order to support backward compatibility with PyCrypto, functions such as ARC2, ARC4, and Blowfish support 40-bit keys. However, we should use considerably larger key space to mitigate the risk associated with a short key space. Some PyCrypto functions are dropped, which can introduce backward compatibility issues. Developers have to make modifications to the code to address these issues. Developers are highly recommended to go through PyCryptodome documentation to get to know which are the functions that have been dropped. Finally, I will discuss about Bleck-and-Decker attack. If a developer is using PKCS1 version 1.5 padding to make the encryption using RSA algorithm, the encryption is vulnerable to a timing variant of Bleck-and-Decker attack. Instead, optimal asymmetric encryption padding should be used. In this slide, I will discuss about PyCryptodome API misuse, where an RSA private key is exported without a passphrase in the clear. If an attacker can get access to the private key, he can import it and the RSA encryption will be compromised. The library designers of PyCryptodome have warned about this in their documentation, and in order to mitigate this risk, developers must encrypt their RSA private key with the passphrase to introduce the necessary security. I have written 2 programs to demonstrate this. The first program generates a key and writes it into 2 files. The first file is without a passphrase and the second one is with a passphrase. The second program reads both the files and tries to import the key. We move to the next slide, which demonstrates this. First, we generate the key and write it into 2 files. We will find that the 2 key files are created. Then we go ahead to read them. We find that the file with encrypted key is not readable. However, the file with unencrypted key is easily readable, hence this is a vulnerability due to API misuse.
So now that we've seen the uses of PySalt, what can it not do? The only legitimate issue with using crypto libraries in Python is its inability to zero out memory, and this is important for eliminating cryptographic secrets when you're done with them. However, this normally isn't that big of an issue unless the attacker is getting a core dump of your endpoints in your retreat model, and also isn't normally plastered all through the memory before even hitting the C binding. PySalt also doesn't have good forward secrecy, usually necessitating the use of a getter for curve 25519 ECDHE shared secrets with other ciphers to derive necessary keys for the forward secrecy with a hash ratchet. This is because PySalt works differently from the other secret block methods like RSA, where normally there is one public key to encrypt for one and one private from the sender. In PySalt, the randomly generated private key is appended to the public key of the message, so normally this is preferable even if it's less secure, since the only lack of support from PySalt could be from using SSL, which currently doesn't support curve 25519. Another issue is the constant time that libsodium implements, but they're not always necessary for the implementations in Python, but again, not a big issue without the core dump. PySalt lacks any serious vulnerabilities since it's so simple to use. There exist some issues, however, as pointed out by the community, like having to reuse a nonce, which is just an arbitrary number used in cryptographic communication. Reusing a nonce could allow an attacker to decrypt other messages. Amateur cryptologists could slip up and reuse a nonce since it's freely transmitted and stored just in a plain text in conjunction with the ciphertext file. However, the nonce requiring functions either use a nonce that's long enough to safely regenerate each time, or it can simply be extended using a pseudo-random function with an extra nonce and key. User vulnerabilities can occur when using a secretly generated PySalt key for symmetric key encryption, and since PySalt uses a 32-char base 64 encryption, the secret key file can be replaced with other keys using a variety of other algorithms. For example, you could use Fernet, PBK, DF2, Script, and Argon2. These are implemented the same way as PySalt by generating a data encryption key, and then that randomized key is encrypted with a password encryption key. So the problem arises when some users could reuse a PySalt key, which could then create security problems from a cross-protocol attack through checking input validation and data encodings from the API's library. So now I'm going to show you an example of code of implementing a secret key encryption in PySalt. So now looking at this code up to the line encoding the message the president will be exiting through the lower levels, PySalt can automatically generate a random nonce for us, making the encryption very simple. So now in this next section, I show you how you could explicitly create a nonce if you need to, and that can be passed along with the message as well. Another section, you could also get the ciphertext and authentication data without the nonce, and then you can get the ciphertext attribute of the encrypted message instance returned by the encrypt method. And finally, in the last section, we can decrypt the message regardless of how the nonce was generated in the previous examples. Cryptography as a field has to constantly be developing new defenses to attackers trying to be one step ahead. The development of cryptographic libraries like the 3 discussed in this paper are the few of the biggest libraries for cryptography in Python applications. Developers rely on these libraries to avoid becoming the target of misuse and vulnerability, and outlining the libraries that have some of the most sound construction and offer primitives that have been proven to be secure is a first step to preventing this. Addressing the issues of developers not understanding the background of these libraries, whether from confusing documentation or the fact that it's written in C when these specific libraries are for Python developers, is another issue in itself. On top of software development, developers need to keep up to date with current issues impacting not only these specific libraries, but information security APIs as a whole, since issues with Java or C++ libraries could have cross effects on the libraries mentioned here. This will help reduce the time developers spend cleaning up after an attack, since they will be able to identify potential threats before they even happen. While cryptographic libraries have come a long way, we outlined some of the best out there, and they still have the ability to be misused, which goes to show why it's important to still remain vigilant. Understanding the documentation and using the best API on a case-by-case basis, as well as avoiding the certain specific pitfalls each library has, is one of the best approaches developers can implement themselves to avoid misuse now and in the future. And with that, I just want to say thank you for watching our presentation, and have a good one. Bye.